Hello everyone, in this theoretical tutorial number 51 we will talk about the basic memory cell, then the RS latch with set and reset priority. We will analyze the RS latch based on NOR or NAND gates, comparing it with the old logic relay. The simplest memory cell consists of two inverters in series with the output connected to the input. The two inverters connected in series can also be shown with the output close to the input. If we force the input into 0 volt, the output out will be forced to logic 1. But now, if we stop forcing into 0 volt, the output out will remain at logic 1. This is a basic memory effect. To change the output state to 0, we need to force the input to logic 1. When we release the input state, the output state remains at 1. This is the memory effect again. To improve the basic memory cell, we can replace the inverter with a NAND gate. With this change, the added logical control of the two inputs will help to avoid forcing the input stage to a specific logical state with a strong force. We can also modify the schematic representation to get the control of both inputs on the same side and both NAND gates in the same direction. Of course, we first decided to replace the inverter with a NAND gate, but we can also use a NOR gate as shown. Now we will analyze the logic using relay. The X contact is driven with a coil noted with uppercase X. When the set switch is pressed, current flows through the upper branch to power the relay, denoted by a capital X. The relay switches on the contact X, so relay X is also powered by the lower branch. Now, when the set switch is released in the open position, the upper branch no longer has current, but relay X is still powered by the lower branch denoted in red. In summary, contact X keeps relay capital X powered, and the relay is powered by the contact X. This is the memory effect. To remove the memory effect, the reset switch must be pressed to stop the current in the lower branch. The relay is no longer powered, contact X is open, so even when the reset switch is released, the relay X remains in the off state. The Boolean equation is capital X equals S or R bar and X. This is the same operation in this other topology with a set switch powering the upper branch noted in red. Then the lower branch in parallel with the set switch is turned on with the X switch driven by the relay capital X. Now, when the set switch is released in the open position, the upper branch no longer has current, but relay X is still powered by the lower branch denoted in red. In summary, contact X keeps relay capital X powered, and the relay is powered by contact X. This is the memory effect. To remove the memory effect, the reset switch must be pressed to stop the current in the branch parallel to the set switch. The relay capital X is no longer powered, contact X is open, so even when the reset switch is released, the relay remains in the off state. The Boolean equation is capital X equals S or X and R bar. In this first analysis, each schematic seems to have the same behavior with set and reset operation. But if we look more closely at the schematic on the left, if we press both the set and reset switches at the same time, relay X is energized by the upper branch even if reset is pressed. We call this topology a priority set. In the right schematic, if we push both set and reset switches, the relay X is not powered because the reset switch stops the current to supply the relay capital X. We call this topology priority reset. The Boolean equation X equal S or R bar NX can be written as a NAND gate with input S bar and R bar X bar. Thus, we can first construct the product R bar NX bar with the first NAND gate with R bar and X as inputs. Then this product R bar NX bar will be used as input for the second NAND gate to create the uppercase X output. The uppercase X output is connected to the X input. Now, for the priority reset, the Boolean equation can be written as a NOR gate with the R bar and S or X bar inputs. So we can first construct the product S or X bar with the first NOR gate with S and X as inputs. Then this product S or X bar will be used as an input for the second NOR gate to create the uppercase X output. The uppercase X output is connected with the X input. The priority set is the input of the NAND with its output noted Q. The priority reset is the input of the NOR with its output noted Q. But for the RS NAND, Q bar is a real Q bar only if S bar equal 1. For the RS NOR, Q bar is a real Q bar only if R equals 0. If R bar equal S bar equal 0, then Q equal Q bar equal 1. And if R equal S equal 1, then Q equal Q bar equal 0. In this last slide, we start again with a basic memory cell with the two inverters connected as shown. Next, we replace one inverter with the NMOS inverter with a red output and orange input. The second inverter is replaced with another NMOS inverter with a green input and blue output. The blue output is connected to the orange input with a light blue arrow. The red output is connected to the green input with a light green arrow. The basic NMOS memory core is duplicated on both sides. On the left side, we add two red NMOS in series, and on the right side, we have two red NMOS in parallel. On the left side, the NMOS in series make up the two NAND 2 NMOS gates. The two added red NMOS allow us to add the set and reset bar inputs as well as the Q output. On the right side, the NMOS in parallel make up the two NOR 2 NMOS gates. The two added red NMOS allow us to add the set and reset inputs as well as the Q output. Of course, with the red NMOS constituting a NAND, it is obvious that if R bar equal S bar equal 0, then Q equal Q bar equal 1 because the red NMOS are in the off state. Of course, with the red NMOS being a NOR, it is obvious that if R equal S equal 1, then Q equal Q bar equal 0 because red NMOS are in on state, forcing Q and Q bar to 0 volt. I want to thank you for your attention. On my next TRC tutorial number 52, we will talk about the RLC oscillator in parallel and series mode. So, see you soon and stay tuned.